All right, welcome back. Today we're going to talk about heat. Heat is the transfer of energy. Let's get this fixed. It is the transfer of energy by the collisions of the particles. Those particles are going to be colliding with each other and they're going to transfer that energy. The symbol for heat is Q, and the unit that we use is the joule. And one important thing to remember is energy is always going to flow from the particles with the greater thermal energy to those with the lower thermal energy. Okay, so they're always going to go from the greater thermal energy, or the hotter particles are always going to transfer their energy to the colder particles. Very important to remember. We're going to be looking at a heating curve. You guys did this with the Icy Hot Lab. And a heating curve is actually an endothermic process, because endo means within. Okay, and the heat is going to flow into the system itself. So if we look at our heating curve over here, it wants us to label the three states of matter and the phase change. So we have our first line down here. This would all be straight up solid. So you can see that that temperature is increasing, so that's going to be the solid. Where you're going to see it kind of plateau, that's where you have the solid and the liquid. So this would be melting. Then you're going to see a rapid increase in temperature again, so that would be your liquid phase. Then you're going to see it level off again. You're going to have that plateau, so you're going to have your liquid and your gas there. And at this time, you would have evaporation or vaporization. Okay, and from there, once that temperature increases again, you will just have that gaseous phase. So you're going to notice whenever you have two phases that there is no temperature increase. Only when there is one phase do you see that there's going to be a change in that temperature, because our temperature is over here. Now a cooling curve is the exact opposite. This is an exothermic process, and in this case, heat is going to flow out of the system. Exothermic, think exits. Okay, heat is exiting the system. So again, now it's going to be the exact opposite. So our first line that we have up here, this would just be that gaseous phase. So you're going to see that gas is going to decrease into the temperature. Once it has decreased enough, it's going to plateau, and you're going to have the gas and the liquid phase right here. And this phase, when you're looking at that, that would be condensing. Okay. Then once you're going to see, once all that gas and liquid is in one phase, now we start to see a temperature cool down. So that temperature is cooling. So you can see that it is going down like that. So we just have our liquid phase. Then that temperature is going to plateau again, and we are going to have a liquid and a solid at that point in time. And that would be our freezing. And once all of our then once we get rid of all of our liquid, we just have our solid there, and then our temperature can go ahead and keep on decreasing. So that is our cooling curve. Now, units of energy. So some important units of energy is the calorie, and this is basically the quantity of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Test question right there, so kind of star that guy. The symbol for that is a calorie. Another unit of energy that we use is the SI unit of energy, which is the joule, and it has a symbol J. And you will have to be able to convert between calories and joules. So basically you can make this into a for every statement. So for every 1 calorie, there are 4.18 joules. So we're going to go ahead and convert our 50 joules into calories. So we have our 50 joules. You can either do this by a proportion, doing the cross multiply and divide, or you can do it just as using your for every statement. I'm going to use a for every statement. I'm not going to use the cross multiply and divide. So we have our 50 joules. If we want to get rid of joules, we're going to put them on the bottom. So we know that for every 4.184 joules, there is 1 calorie. and joules can now be crossed off. So you have to make sure that you put your units in places where they can be crossed off, and you'll get 12 calories. And I can't fit the calorie on there, so we'll put calorie. Okay. Next up, we are going to convert our 34,000 joules into kilojoules. Now, this is another one. We're not switching in between calories or anything like that, but we're just switching our prefixes. So we're going from a calorie to, or a joule to a kilojoule. So one important thing to remember, we learned this in our first unit, is that 1,000 of our base unit, so 1,000 joules equals 1 kilojoule. Okay, so we still have this in a way that we can cross out our units. And our answer in this case, we would take our 34,000 divided by 1,000. We're going to ignore the 1 because anything multiplied by 1 is itself. So we would end up getting 34 joules. So next up we have our heat equations. And these are going to be the important calculations that we are going to use throughout the unit. So first off, we have specific heat. And its symbol is C, and basically this is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Again, very important definition that you need to make sure you know there. The units, another important thing. It's kind of lengthy, but it is a joule per gram per degree Celsius. So another way you can write this would be the joule is over your grams degrees Celsius. Okay, so joules are on top, grams and degrees Celsius are on bottom. We're going to be using an important equation right here. So we're going to be using an important equation right here. We have our Q equals MC delta T. So Q is the heat in joules, M is the mass, C is the specific heat, and T is the temperature change. Now, whenever you're doing a temperature change, it is always T2 minus T1. So it is always your final minus your initial. Very important to remember there. So a couple of questions that we have dealing with this. Lead has a specific heat of 0.13 joules grams degrees Celsius. And what does this mean? Basically, this means that it's going to take, for every 0.13 joules of heat, you're going to be able to raise the temperature of 1 gram by 1 degree Celsius. Okay, so it's going to take 0.13 joules of heat to raise the temperature of 1 gram by 1 degree Celsius. And what is going to heat faster, lead or water? It is actually going to be lead is going to heat faster because it has a lower specific heat, which means that it's going to require less energy to heat it. So another example that we have is, and this is going to be for this guy right here, is we have when 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85. We want to know what that specific heat is. So we're going to use that over there. So I'm going to move this up a little bit so it's going to give us a little bit more room. And we're going to get this set up. So remember, we're going to use this equation right here. So we're going to use our equation right here. So we know our heat, our Q, which is 435 joules, equals, we know our mass is 3.4 grams. We're looking for, we don't know what our C is, so that's our unknown. So I'm going to go ahead and put this in a different color. And then our delta T, we have to figure that out. So our delta T is going to be our final, which is 85 degrees Celsius minus 21 degrees Celsius. Okay, so when we go ahead, we've got to solve for that. So we have our 435 joules equals our 3.4 grams. We still don't know what our C is. That's what we're trying to find. And we know our delta T, 85 minus 21, that is going to be 64 degrees Celsius. Now, because these are all multiplied, we're going to have to go ahead to get rid of them onto the other side. This is just basic algebra here. We're going to divide both sides by our 3.4 grams times that 64 degrees Celsius. So 3.4 grams and 64 degrees Celsius. So that causes those to cross cancel out. And then we don't get to cancel any units out over here. So our final answer is going to be left with our joules, grams, and degrees Celsius. And our final answer, so our C, once you go ahead and calculate that out, C ends up being 2 joules per gram degrees Celsius. All right, next up we have our heat of fusion. Heat of fusion is the quantity of heat required to melt or freeze a substance. And heat of fusion is given the symbol F, HF, and its unit is a joule per gram. The equation is Q equals the heat of fusion times the mass. And we'll talk about why there is no temperature change in there. So that's really important. If we even look back, if you start thinking about those heating and cooling curves, remember we talked like, hey, when that temperature is plateauing out, there are 2 phases in there. So this is where that's coming into play, that heat of fusion. And then the heat of vaporization, that's the heat required to evaporate or condense a substance. So again, you're undergoing that phase change. So it's kind of like our heat of fusion that's going up on there. The heat of vaporization is an HV, and again, it is just a joule per gram. And the equation, very similar, is the Q equals that heat of vaporization times the mass. So we have our example here. Water has a heat of fusion of 334 joules per gram. What does that mean? That means it's going to take 334 joules of heat to melt or freeze 1 gram of water. So for every 1 gram of water, you need 334 joules of heat to melt or freeze it. So an example here is how much heat is required to melt 25 grams. So we're going to use our Q equals, we know since it's melting, we are going to use our heat of fusion. So 334 joules per gram. And our mass is 25 grams. So we're going to cancel those guys out right there, and you end up getting an answer of 8,350 joules. Okay, so saying, hey, that's the only thing that's left right there, so that should make sense. So now, which equation to use? So when are you going to use the delta T, and when don't you use the T? Easy one right here. I'm going to do it in 2 different colors, so that's why it's going to be easy for you guys to see. So first off, we're going to see the thing that you have to look for is look for when there's that temperature change. So when you're going to use the Q equals MC delta T, or MCAT, you're going to look where there's a temperature change. There is a temperature change here. There is a temperature change here. There is a temperature change here. Okay, so that's when you're going to use that. Notice there's only one phase. You're only going to have solid, you'll have liquid, you'll have gas. Now, when you use the other equation, so when are you going to use the just Q equals HM? Again, no temperature change. So you're going to see that when there is a phase change. So you're going to see that here, and you're going to see that here. So there is a phase change going on. So you're going to have the solid and the liquid, and then you're going to see that you have liquid and gas. So that's where it's going to be boiling at. So since there is no temperature change, that is when those particles are going to be requiring that extra boost to be able to jump out of a phase. Go ahead and take a couple of moments and write your summary of what we talked about today. And that is Unit 3 for heat.